So we're gonna go over a proof of Green's theorem. Well, maybe not a complete proof, but maybe we could try to get some intuition of Green's theorem. So Green's theorem is this idea that there's a curve, C, and this curve is simple and close. So simple and close. And it defines the region R. And suppose that we give the curve C an orientation, right? It would be counterclockwise. So imagine that we also have a vector field F, right? So, and suppose that the curve is described by a function R. Then it's equal to the region enclosed it, defined by R. And it's going to be, so by the way, let's assume that this vector field is describable by M, X, Y, and then I plus N, X, Y, J. Then it's going to be N, X, the partial with respect to M, with respect to Y, dA, where A stands for area. So the idea behind this is that, if we integrate the vector field along this curve, this closed curve, it will be equivalent to taking the integral of the region within the curve. So sort of like imagining that this is the curve C, and we can imagine that that this is the area that we're integrating. This is the region R. You're integrating this region, right? So one way to think about this is to think about this region as made up of tiny little cubes, like maybe not cubes, but rectangles, right? That are dy and dx, and that by taking the double integral of all of these tiny little areas within R, right? You get the total region R, and that this whole thing is equivalent to taking the vector field along the curve or the circulation. So this is Green's theorem, okay? Maybe this is not a complete proof, but here's the intuition behind this. If you have a curve, right, counterclockwise, of course, the one assumption that we should have is that the area of defined by the C is R, and that R is the sum of tiny rectangles. defined by delta x and delta y. So that region R can be approximated by like a summation of these areas. These maybe some number times delta x delta y, right? For maybe you want to have infinity number of these squares that can approximate this region R. This is the first assumption. And the second thing is the intuition that, so again, imagine we have a simple closed curve C, and that's counterclockwise, right? So do we have some intuition of why the circulation on the boundary is the same as the integral of all the areas within the C? Well, consider the following. Suppose that we are able to cut the curve C in such a way. So in such is the case, right? Suppose that we are able to cut this curve C into two, and do this cut, we now have two curves. So the curve is here. So the first one, the top right, is still counterclockwise. So the curve is going down like this. Whereas for the bottom left part of the curve, right, you have like this. So notice that the arrows are in opposite direction. So they are anti-parallel with respect to each other. And because of that, they cancel out. They cancel out. And so you have a single curve. So you have originally you have a curve C, and you cut it, and then you have two curves. But the internal boundary in which the new curve, the boundary in which the two curves coincide, they match each other in length, and they cancel each other out. So all that really matters is really the outer boundaries. So all that matters is this part, the circulation, right? And what's between has canceled out. So if now let's suppose that we imagine, let's give another example. So imagine that our curve C is actually a rectangle. Right? And imagine it's counterclockwise. Imagine we have a cut. And as a result, we form two curves. So it's still gonna be here. We're gonna close this. This part on the right goes down, and this part goes up. Again, they cancel. The two sides cancel. So the circulation cancels in this part, this side, and that side. So the only thing that contribute to the curvature is this part, the outer part. So this would be the intuition for Green's theorem. Now, we're going to imagine ourselves to so remember that suppose we have a curve C, right? And then we have, this looks very ugly. Let me just draw this more precisely. So imagine we have C, and imagine that we are able to break up this region R. So what's inside is R, or the region R, right? And as the region R is defined by a simple closed curve C, and suppose that R can be approximated by these rectangles. So basically this delta x and delta y's. We would like to, calculate what is the curvature of this tiny little region here, right? So let's begin. Suppose that we are at the origin, and that this is x and y, and suppose that this region is going to be x plus delta x y. Sorry about this. Right. This is going to be, let's draw this rectangle. So the side here is going to be defined by delta x. This length is also going to be delta x. This is going to be delta y. This is also going to be delta y, right? Suppose that, oh, by the way, this is going to be x plus delta x, y plus delta y. Okay, and then this point here is going to be defined by x plus delta x, y. Okay, and suppose that our C is going to be counterclockwise. We would like to know the circulation around C, right? So let's do this. So the circulation around C would be F, right, times delta dot dr, but that's just the same as m delta x n delta y. And let's suppose that we could break this curve C into C1, C2, C3, and C4. So what we have is that this whole thing is equal to C1, C2, C3, C4. Let's look at C1. One thing that stands out when we draw this rectangle is that there is a certain sense of symmetry. The C1 and C3 is changing with respect to x, whereas the C2 and C4 is changing with respect to y. So let's focus on C1. Since the only change is the change in the x direction, we don't have to care about the n part of the vector field. We only have to care about the m part of the vector field, right? Times dx. And, well, we're gonna look at, so the change in distance will be delta x, and we're thinking about m, right? We're thinking about really the m times x plus delta x y times x, right? Because it's moving in the right direction. But notice that as delta x approaches 0, that's just the same as m x plus y delta x. Similarly, let's focus on C3. We're going to go in this direction, right? We're gonna go in the left, right? And we're thinking about this value, right? As delta x approaches 0, that's gonna be our vector field. We're gonna focus only on the m direction. It's gonna be x plus delta x, and then y delta y, and then we're gonna look at the opposite direction, delta x. It's going to be as delta x approaches 0, x. So let's see. Yeah, this is it. Let's look at C2. And because C2 is really changing in the y direction, we don't really have to care about the the m part of the vector field. We only have to focus on the n part of the vector field. Right? And it's going to be n. So x plus delta x and then there is y plus delta y, but as delta y approaches 0, that's just going to be y times y as delta y approach 0. C4 that's going to be n. It's this part is a bit mistaken here. This part, I think there's a mistake. So this is going to be y delta y. So as delta y approaches 0, this is going to be x plus y, right, times negative of delta y, because it's going down in orientation. The C2 is going up in orientation, so it's positive. C4 is going down, so it's negative orientation. So this is what we have. We could try to put it all together. So let's take a look at, focus on just the C1 and C3, right? It would be something like, all right, C1 is going to be m x y delta x, and then C3 is going to be negative m x y delta y delta x. We could pull out the delta x and maybe pull out the negative. And what we have is x, y, delta y minusing x, y, delta x. This looks very much like the definition of a derivative. Or it looks like a partial derivative of. It seems like a partial of m with respect to y, right? So we can make some sort of generalization and to say that delta y approaches 0. And what this whole thing is will just be partial of m with respect to y. And then you have dx, dy. Now let's try to do the other one. This time C2 and then C4. C2 is going to be C2 is going to be this. This one, and then C4 is going to be this one. We're gonna add them, of course. Right, and you can see that you have n x delta x y minusing n x y. You pull the delta y out. We can see that this is very similar to the definition of the partial derivative with respect to x, right? So we can say the limit of as delta x approaches infinity, delta x, y, delta x, and then this is going to be delta x and delta y. This would just be the partial derivative of n with respect to x, delta x, delta y. So putting it all together, so you have the closed loop C of f delta r. So f dot r, delta r, is equal to the partial of n with respect to x minusing the partial of m with respect to y, delta x, delta y. But since the whole curve is really made up of tiny little small rectangles, right? You could imagine it as this entire curve C. So this C is a small c. This is a curvature around this tiny little smaller infinitesimal rectangle, right? But if you can think about this whole thing as made up of, imagine that big C is encloses this bigger region R, and the region R is composed of these small tiny rectangles. Then you can kind of imagine that, okay, you have a summation of I equals 0, and then you have an infinite number of these rectangles, right? And you have n, right, respect to x, I minus delta m with respect to y, I, and then you have delta x, I, delta y, I, and as this is just the definition of the double integral of r, right? Delta partial of n with respect to x minus the partial of n with respect to y dA. Okay, so that's a proof of Green's theorem.